everyone, welcome back to another video for the series. I'm Q, and today I brought a geometry problem from USAMO. When I first tried this problem, I was not able to solve it, but when I looked at the solution, it just felt so amazing to me because it was like somewhat elegant. It felt somewhat elegant to me, but for some of you watching this video, I think you might think it's quite straightforward, like to think of it this way, but at least it was quite amazing for me, so I wanted to introduce it with everyone. So here is the solution. Uh, so when we draw it, we have an acute triangle. ABC. So here is A, here is B, and here is C. Now rectangles BC, C prime, and B sub 2. Oh wait, did I say C prime? I think it's C sub 1 and B sub 2. Then we have B sub 2 here, C sub 1 here. A sub 1, C sub 2, so we have A sub 1 here. And A sub 1 here, and C sub 1, C sub 2. And finally, before we draw our last one, let's use this one first so that we can have a little more accurate drawing. C sub 1, A sub 1, B sub 2. So this one, C sub 1, B sub 2. So let's say that they just meet around here somewhere. So when we go it this way, we can go it maybe here. Oh, why is it so? Yeah, maybe more like this. No. And B sub 1 and C sub 2. So we should have something like, you know what, I think my drawing is not accurate anyway, so I think I can just draw it. B sub 1 and A sub 2. So we have no, we have B sub 1 here and A sub 2 there. So why can't I draw it? It's actually really no, I don't really care about my drawing anyways, so I think I can just B sub 1. We have B sub 1 here and A sub 2 here. A sub 2 here, and so when we connect these two, this one and A sub 1, B sub 2, C sub 1 and A sub 2, they're concurrent. This is a point. Okay. Now we know that B sub 1, C sub 1 and C So this angle plus C A sub 1 and A. So this angle A B sub 1 and B. A B sub 1 and B. So this angle, these sum up to 180. When I first looked at this problem, I automatically thought of Bryanshans theorem, because Bryanshans theorem states that if we have like an hexagon, 1, 2, 3, 4, 5, 6, so this is a hexagon, and if we have a conic section inside here like this, then we can say that, so if we just prove that there is a conic section inscribed in this hexagon, then we can say that by Bryanshans theorem, these three lines are concurrent. But I think even though most Olympiads allow us to say like by Bryanshans theorem, but if that doesn't like feel right, then I think we can just use radical axis. I forgot how to prove it, but I think the proof went something like this. And if we just use this one, then we can simply prove it. And I think this proof is also possible during the test. It's not like, I remember it being quite simple. So what am I saying? I think I accidentally erased something. So we can use this one, this one, this one, and this one. It's like drawing a fidget spinner, and if we prove it using radical axis, then we can prove it. So I was trying to find a conic section that is inscribed in here, but I was not able to do it. So that was quite unfortunate, but that's what happened. But I found when I first looked at like the official solution, I was quite surprised of its like elegance. Like, so what the solution says is that, okay, let's say that this point is P, and let's draw a circle like this. But before we know that this P is like the point here, so after drawing these three circles, let's just say that the intersection of these two circles that are not C be P. So this point. So the intersection of these two circles that is not C is called P. That's how we define P. Now notice that by looking at this one, this quadrilateral, we know that this angle is right angle. And similarly, we know that by looking at this quadrilateral, we know that this is also right angle. In other words, P is in A sub 1, B sub 2. Now, because this is symmetric, no, I will say because this is just an example, we can say that without loss of generality, we found that P is on this line. That means it is automatically on the other lines. We don't really need to think about other cases, because just think of rotating the triangle and we'll get the same case anyway. So we have it is on this line, so p sub 1, c sub 2, and p is also on, so we did this one, and this one. So which line is this? Is this point a sub 2? A, B, B sub 1, A sub 2. So C sub 1 and A sub 2. That means P is P is the intersection of A sub 1, B sub 2, and B sub 1, C sub 2. But it is also the intersection of these two and these two. That means we can write it like this. Therefore, these 3 points concur at the point P. These 3 lines. So we actually didn't use the fact that we didn't actually use this fact, and I just found this solution really amazing. So I wanted to introduce it with everyone. So if you also enjoyed the solution, please don't forget to like and subscribe. Then tomorrow I'll come back with another very fun problem. Thank you and see you tomorrow. Bye.